to 2013 and 2016, 17. And then the second part will be looking at the use of this fluid in a true triaxial frame and compare this fluid performance in terms of fracturing, of rocks under representative enhanced thermal system conditions, how they compare to the typical water usage as a fracturing fluid, the waterless fluid, which is CO2, and then a combination also of water and CO2. So with that, I will start with changing the slide. So, like I said, part one would be introduction to steam frac, and that's the name we put to the fluid. It's a trademark right now for PNL. Oops, sorry. Right here. So steam frac is, like I mentioned before, is an aqueous solution of polymer. It's a polyallylamine. It's a polymer that we use. We can use some other fluids, other polymers that can react with CO2. The reaction is a Lewis acid-base reaction, where CO2 cross-links the amine of the polymer in the aqueous phase, and when mixed with the aqueous phase, forms a carbamate intermediate that that reaction is triggered by temperature, and at higher temperatures we can see the rates of reaction are faster. So it's an endothermic process, and the end result of that reaction is the formation of a network, basically a viscous fluid or shell that expands in volume. So we thought, okay, maybe we can use this fluid to fracture rock and at high temperature and use the work that this expansion in volume can generate to do this more efficiently, maybe use less water, maybe replace part of that water with CO2. And that's was the reason why we proposed this fluid for enhanced thermal systems and hydraulic fracturing. So you can see the slide. This is slide number 4. It shows we design and develop with EMSO a high pressure, high temperature rotor for magic angle spinning NMR. And what it does is when you mix the CO2 with the aqueous solution, it can determine if there is changes in the CO2, in the carbon of the carbon dioxide, as well as changes in the polymer, like you see here. These are changes in the carbon of the polymer that goes. Sorry, that's the changes in the carbon of the CO2 that goes from a CO2 free molecule to a carbamate that can form. Basically, it's a salt. Carbamate, ammonium carbamate, that is responsible for that cross-linking. If there is dehydration reaction, so this molecule lose water, then we end up with the urea linkage. So this is just to show you that indeed CO2 reacts with the polymer solution, being acid-Lewis reaction, forming a carbamate intermediate, in some cases also dehydration to an urea linkage. And what is the actual microscopic result or observations? Well, this is what you see here is a transmission cell. So you have two windows, one on one side of the cell and the other one on the other side. It's a 9 milliliter cell. And the dotted lines is an aqueous solution of the polymer. So at the beginning, we have air and vapor pressure of the water that is different at different temperatures. So we put the cell at different temperatures, and then we introduce higher and higher concentrations of pressures of CO2. At the beginning, no CO2 added except for the whatever is in the presence of air. And then as we increase the pressure of CO2, particularly higher temperatures in the order of 150 to 200 Celsius, we see that there is a reaction. The reaction takes place in about 20 to 30 seconds. It highly depends on temperature. And But with that reaction, we also see a volume expansion, increasing the aqueous phase volume expansion. And at temperatures as high as 330 Celsius, we see that for 200 atmospheres, so this is equivalent to 3,000 psi, the volume of the aqueous solution is completely is filled in an entire cell. So this is one of the observations of the microscopic properties that we observe upon the reaction of CO2 with the polymer solution in the aqueous phase. And we also measure this up to 400 Celsius. There is a paper in Green Chemistry where we show reactions at different temperatures in addition to these three here. Obviously, like I said before, together with the changing volume, we see a change in viscosity. So the viscosity of the fluid increases for the PNNL fluid as compared to, for example, sodium dodecyl sulfonate or xanthan. These are typical surfactants used in the oil industry, where the viscosity doesn't change with the pressure of CO2, but it did change for the polymer solution upon reaction. It's also a shear thinning fluid, so the viscosity dramatically increases as the shear rate reduces. And we did tests to understand if this change in volume is reversible. And what we understand is reversible not only with pressure swing, like you see here, we increase the pressure of CO2 at 300 atmospheres. This was done at 330 Celsius, and we see a volume increase. But then when we depressurize, the volume goes back to the original value. So the polymer cross-link with CO2, but does it in a reversible fashion. Then we can pressurize again, and we get a volume expansion, and we can reduce it again. So in a way, we can generate changes in volume and in principle in the subsurface, and then generate a fracture, and then we can recover that fluid as a surfactant solution and potentially recycle the CO2 injected once the CO2 leaves the solution upon the cross-linking. So it's the volume expansion and the change in viscosity are reversible. We did obviously control experiments where we have only water, not polymer solution. And even at 300 Celsius, 330 Celsius and 300 atmosphere, we don't see an obvious change in volume. So yes, we say, okay, we can, like I said before, we can use this change in volume potentially to generate work in the subsurface, in addition to the brutal force that we use by injecting high pressures and high volumes of water in the subsurface to generate fractures. So we designed this system. This is a flow reactor here in the middle, and the rock sample goes inside a cradle, and then that cradle goes inside this reactor. This reactor is filled with water, and the sample has a wellbore that is blind. It goes halfway. This is a sample about 2 inches in length by 1 inch in diameter. And what we did is pressurize the sample with water isotropically. That will be the confining fluid to basically simulate the pressure that a rock will undergo at, let's say, 5,000, 7,000, 10,000 meters. And then we injected water or polymer solution, and followed by injecting CO2 to generate the fracture. So first we add about 200 microliters of polymer or water as a control experiment, and then we add CO2, the constant flow rate, until we see that this pressure gauge and this pressure gauge equilibrate, meaning the fluid has broken and the sample has fractured and the fluid has communicated from the inside the wellbore to the confining fluid. So we did this for we did 5 experiments with diorite rock. This obtained from the Costa geothermal field in California. And we did 4 additional experiments with a polymer solution. So instead of injecting first polymer solution, we injected water, okay, in the experiments, and these are results of the pressure, the effective pressure required to fracture that rock. So this is the pressure or the overpressure required to see a communication between the two, the wellbore inside and the confining pressure. And what you can see is that when we use water without the polymer, the average net pressure is about 4 megapascals. Sorry for the changes in unit, but 4 megapascals is somewhere about around 600 psi. When we use polymer active solution, we get values similar to water, but in some cases, and this is because of the sample variability, the rock is not an homogeneous material. In some cases, we get very low, we require much lower overpressure to break it. And in some cases, we require somewhere intermediate, and in others, similar to what we use, the pressure we require to fracture with water and CO2. So we say, okay, well, this could be due to the sample variability, the heterogeneity of the rock. But we do see an effect, right? For water CO2, no changes it's fairly constant, and it's about, in average, 4 megapascal, and the sample variability, one standard deviation, is fairly small, while when you the rock is different. So maybe different mechanisms take place when you fracture with polymer solution CO2 due to the reaction, while when we fracture with water CO2, those mechanisms don't govern the fracturing process. So instead of using a rock, we say, okay, let's use a more homogeneous and predictable material, and this is fused silica. So fused silica can, under the conditions that we tested this fluid, which is 200 Celsius and 3000 psi confining pressure, we anticipate, we actually calculated the value at which the material will fail, and it was about 24 megapascal. When we fracture with water, and these are triplicates, the values at which the overpressure value of the effective pressure at which the material will fracture, so this is the pressure above the confining fluid pressure, to be able to fracture, were in the order of 22 to 23 megapascal. Similar was with hydrochloric acid, the typical fracturing fluid for oil and gas, as well as in geothermal, but particularly in oil and gas. And then a waterless fluid, just CO2 alone, also fractured with a larger standard deviation, but similar or close to the values that we predicted by taking into account the mechanical properties of fused silica. And then when we use water CO2, we have more variability, but we see a small change or lower values on average as compared to other 3 fluids. And when you use the polymer solution, the values are even are significantly lower with respect to the values obtained for water. So indeed, what we propose here is, okay, if we're fracturing at lower pressures, but the system is open, the only way that this additional pressure to fracture, because you need this pressure to fracture, or at least this pressure, if we're measuring less values of pressure, maybe we have a shell formed that plugs this wellbore and generates some radial stress that the pump, several feet away from this rock, don't see. But it has to be a shell that will have a high shear stress, so it doesn't break when the volume expansion takes place and forms this localized overpressure. That was our hypothesis. Oops, we cannot see the system here, but let me see if I can see it. Okay, here we go. So to be able to measure that overpressure, what we did is we designed and built a system that is basically an airflow reactor that is separated by a piston with 4 plugs. The piston will have 4 plugs that can fall down when we move a rod. And the rod is not seen here, but there is a rod that will move the piston one side or another, and those plugs will fall down and will enable the mixing of one fluid with the other one. And why we did this? We wanted to have a closed system with zero volume change when we mix, where we have polymer solution or water on one side and CO2 on the other side. So then we say, okay, if there is water mixing with CO2 and there is no volume expansion, if the system is closed and we have the pressure before and after, we can see that there will not be a change in pressure other than just associated to the solution of the CO2 into the water solution. Maybe a decrease in pressure, maybe an increase, but it will be definitely not the pressure measured by a volume expansion associated to the reaction. So what we did was put either water here or polymer solution, and in this case always CO2, and then we move the piston, those plugs will fall down, the fluid will mix, okay, and then we will measure the pressure on both sides of the cell. Is basically once they mix, obviously the pressures are the same in both sides, and the results are that for water, when we have only water and we mix it with CO2, a different volume of CO2, yes, as you increase the pressure of CO2, you will have a higher pressure. But when you have polymer solution mix, yes, also the pressure increases, but increases at the higher value for each volume of CO2 added. The pressure differential is, to us, the overpressure or the work associated to the volume expansion. And those values were in the order, depending on the concentration of CO2 in the cell, were in the order of as low as 100 psi to as high as about 1200 psi. And those are similar in average. Again, these are 200 Celsius. The experiments were done at 200 Celsius, but on average, these values are more or less similar to what we see, the difference in pressure required to fracture fused silica as compared to fracturing fracturing fused silica with just water, not the PA that reacts with CO2. So we say, okay, we were able to measure the overpressure associated to this, and we say, okay, we have quantitative evidence that CO2 trigger volume expansion of aqueous PA in confined environments can generate work. And we published this paper on ACS, Sustainable Chemical Engineering. So then we said, but we were not convinced how this localized pressure can be formed, how a plug, and I will show this in the next slide. If you have a wellbore and this is a rock, and let's say we have the formation of a shell, and then this is a reactive fluid. This shell has to basically not move whatsoever and basically generate radial stress without breaking or without just being displaced by the overpressure radial. So we did some modeling to measure or to determine the elastic. Well, we treat this shell as an elastic solid, and we determine using viscosity measurements the bulk modulus of the material, and based on that bulk modulus, a 35% increase in volume expansion, let's say at 200 Celsius, about 50%, but let's say 35%. What would be the pressure if that shell would not move, if that shell was not destroyed by the volume expansion? It would stay there. The overpressure was very small. It's in the order of 0.02 psi, nothing. Basically, in a nutshell, these measurements and we use viscosity. I don't have the results here. I didn't want to go into more detail, but measuring shear stress versus shear rate, we got the bulk modulus, and what we got out of that is a value of the radial pressure upon volume expansion for that bulk modulus values. And what we get is a very small overpressure. It's very, very small, not something that you can measure. So the formation of a plug does not explain, will not explain the lower oil pressure required to form, to fracture the rock and to fracture fused silica, because those radial pressures that we measure based on viscosity analysis are very, very small. Now, the viscosity was measured in a 23 milliliter cell, and the volumes that at which this potential plug would have formed were in the order of 200 microliters. So we know that volumes, different volumes can change the rheological properties of fluids. So maybe the way that we measure the viscosity was not to determine the bulk modulus, is not the way to do it. But in either case, we do know that the values of overpressure measured for water, for CO2, for hydrochloric acid are very similar to the predicted ones based on the mechanical properties of fused silica. So we do know that we observe a lower overpressure for PaCO2. What we cannot say is it associated to the volume expansion and the formation of a plug and a localized pressure, radial pressure? We cannot say that with these numbers. So we needed to move in this project, and we had it as a follow-on project, phase 2 of this project. And what Geothermal Technology Office was interested in is in looking at, okay, it looks like the polymer solution with CO2 outperforms other fluids in terms of the amount, the pressure required to fracture either rock or a material like fused silica. Okay, can it also generate fractures with higher conductivity than water or CO2, which is a fluid that a lot of people are using right now? And also, can we perform this work in a more representative environment? And when I say more representative environment, the rock usually in the subsurface is not subject to an isotropic pressure. The pressure is different in different directions. So what we used was a true triaxial frame. And we also wanted to find out if this water saturation of the rock, because you will find in different regions of the United States and also in the world, the rock is saturated with different levels with water. So how that water saturation can impact the performance of the fluids, and is that impact associated to a change in mechanical properties of the rock because of the different level of water saturation, or is it associated to the mechanism of the fracturing itself for each fluid? And why it's important? Like I said before, because they are in different places in the United States. You have different saturations. You can go from 3.6 to 24.8 in these geysers, but we have also seen in other ECS systems, enhanced geothermal systems, saturations significantly higher of 24% of water in the rock. Oh, sorry about that. So this is a rock sample. Well, this drawing is a cubic rock sample of 6 inches in size, or half a foot in size, and then we make a wellbore. We generate a wellbore. It's not blind. It goes all the way through the center of the cube, and then we put puckers, one on top and one on the bottom of 2 notches that we create on the rock sample. Why we put these notches? To guide the fracture in this direction. The only way to do it is using a notch, and also by applying pressure, vertical versus the 2 horizontal in this direction and in this direction, lower. So the vertical load is lower than the other 2 loads. Unfortunately, you cannot see here, but it's 1100 psi for the vertical and 1400 psi in both this direction and this direction, X and Y. So by having a minimum principal stress in the vertical direction, we are guiding, or we are enabling the fracture to generate on the horizontal or perpendicular to the direction of the injection of the fluid. So we built this system, and I don't have pictures of it, but trust me, it's a very complex system where we use flat shocks using pumps to put pressure on all sides of the rock, except for the vertical side that we use a frame, a loading frame. It's a mechanical piston that pushes the rock down, and then those, by having controlling all three stresses in all three directions of the rock, we have a more representative condition of what the rock will undergo in the subsurface. The experiment were done at 200 Celsius, and like I say, confining pressures of 1100 and 1400 psi, 1100 in the vertical and 1400 and 1400 on both horizontal directions. We tested water, we tested CO2, and we also tested single cycle water CO2 and single cycle polymer CO2. We did more experiments, but we're going to focus today on these ones. So the way we saturated the rock was very simple. We just fill the system, including the wellbore, with water at 1000 psi, and we maintain that pressure. And then we just let the water to transport inside the rock sample for no days, so basically no saturation whatsoever, 1 day and 3 days. If we want to fracture with water, then we follow with a constant flow rate of water. Okay. If we want to fracture with CO2, we don't introduce water. We follow with CO2. If you want to do a cycle of water and CO2, or polymer solution in this case and CO2, what we do is we inject about 1/3 of the total pore volume of the rock, which is about 12 milliliters of water. Okay, taking into account the porosity of the rock is about 2%. The weight percent, sorry, pore is about 2% of the rock is porous. And then we inject 1/3 of that, and either water or PA, and then we follow with the injection of CO2. If we want to do multiple cycles, and that is something that we will do in the field, we try here as well, but we were not successful, and the reason for that is we had to inject at a very low flow rates to avoid that this fracture distribution doesn't occur so fast. So we have time to inject fresh CO2 and fresh polymer or water every time as the fracture propagates. We were successful in doing that, but we were not successful in getting a fracture that can be measured. So this is something that we will do in the field. How? Because the idea here is, if we can fracture more efficiently with polymer solution, with steam frac basically, and CO2 by reaction, how we can propagate those fractures hundreds and hundreds of meters away from the wellbore. We don't care about if we can generate a fracture in the wellbore or close by. We care about being able to communicate two wellbores, a production and injection wellbore, by propagating the fracture hundreds of meters into the formation. So that was the idea. But in this case, we just stay with a single fracture, a single cycle, okay? One polymer solution, and then followed by constant flow rate of CO2 until the rock fracture. And how we know the fracture? Well, you see that the pressure, there is a pressure drop, obviously, because the fracture has communicated all the way to the surface of the rock. And what we observe is that for water injection, just using the typical fracturing fluid, is conventional water. Sometimes they use brines. In this case, we use just tap water. What we observe is that the breakdown pressure increases with the flow rate, but and it does not change much with the water saturation. So this is dry rock, and this is 3-day water. And so Yeah, there may be a decrease in the amount in the breakdown pressure, in the pressure required, over pressure required to fracture the rock, but it's more or less similar for different flow rates to what we observe in dry hot rock. In terms of conductivity values, independently of the flow rate at which we inject the water and the saturation of the rock, either dry or with 3 days pre-water saturated, the conductivity is very low in all cases. And the mass consumption is observed here, and it also doesn't change with the flow rate used, but it does change with the presence of water. So we consume much more water to fracture the rock when we have a water saturated rock for 3 days. If we use CO2 as a fracturing fluid, what we observe is that the breakdown pressures are similar to water. Okay, independently, it may increase a little bit with higher flow rates, but when you go and you inject CO2 in a already saturated, water saturated rock, we see that there is a decrease in the breakdown pressure. In terms of conductivity values, we see a lot of variability, and we don't have here the error bars, but it's crucial for CO2 that the flow rates are high, 10 milliliters and higher for dry hot rock. If not, we don't see basically the fracture conductivity is very low. Below 5 milliliters per minute, we see no fractures, or we just cannot observe it after post-mortem. And also when we measure the conductivity post stimulation, is very low, very similar to water. But in some, when you have higher flow rates in dry hot rock, the values are high, but they vary a lot. And this is potentially due to the changes from sample to sample of the of the mineralogy and the porosity of the rock. That's what we observe with CO2. And when we do perform the work, a stimulation or fracturing with CO2, and in water saturated rock, either 1 day or 3 days, there is no way we can fracture at flow rates below 25 milliliters per minute. So this is the maximum flow rate we can achieve with the pump, and we needed to do that to be able to fracture. And even with those flow rates, in particular in the 3-day water saturated rock, the conductivity values were very small. And this is the mass consumption of CO2. And again, the trend is, if we fracture at 25 milliliters per minute, the trend, and again, we haven't done this at hot dry rock, will be that you require more CO2 as the rock is more saturated with water. If we introduce water, it's 1/3 of the total core volume. After we've saturated with water, we introduce 1/3 more, so 12 milliliters of water, followed by injection a constant flow rate of CO2. What we observe again is that in hot dry rock, the overpressures required to fracture are higher than in water saturated rock. The conductivities are higher for hot dry rock as compared to water saturated rock, particularly water saturated rock for 3 days. And the mass of CO2 is similar to what we observe when we use only CO2, is higher for a water saturated rock, the amount of CO2 that we require to fracture. And finally, we did a cycle with polymer solution. Instead of water, we inject 11 milliliters or 12 milliliters of PAA, polymer aqueous solution, 1%. And we did those experiments followed by CO2 injection at constant flow rate. And what we observe here is breakdown pressures similar to water, similar to CO2 with water, similar to CO2 alone. So there is, like in the presence of, in the smaller samples that you observe that you require less pressure to fracture. In this case, we don't see changes. It's either same or even higher in terms of overpressure required to fracture. But, and then it doesn't change much with the water saturation. What it does change, and this is similar to what we observe with CO2 in water, is that hot dry rock, even at in hot dry rock, the breakdown, the conductivity values are high and are significantly higher than in water CO2, as you can see on the previous slide. This is about 15 cubic micrometer versus somewhere in the 60 to 80 cubic micrometers. And then for water saturated rock, it's also very high, the conductivity. But when you go to water saturation of very high water saturation rock, like in the case of water, like in the case of CO2, like in the case of using water plus CO2, the conductivities are low. And this is the mass of CO2 used for PA CO2. We did some thin sections of the samples, and this is for hot dry rock. We are still pending the thin sections analysis of the water saturated rock. And what we observe is for steam frac is this sample. For water, the fractured rock, this is a picture of the thin section, and we can barely see the fracture. Like this fracture is volume is in the order of 0.8 to 1.7 cubic micrometer. Independently of the flow rate, 2 milliliters per minute or 25 milliliters per minute, the fractures are very small. The fracture conductivity are very small as well. When we use CO2, it's all over the place, but on average, it's in the order of 10 to 23 cubic micrometers. So CO2 is more efficient fracturing rock, hot dry rock than water. And when we use a combination of water followed by CO2, again, similar, maybe slightly higher on the upper end compared to CO2. But when we use frac, the polymer solution with CO2, the fracture aperture is significantly higher, and it's independent, and this is very important, independent of the flow rate, injection rate. We can use 2 milliliters per minute here. We can use 10 milliliters per minute. We can use 25 milliliters per minute. And the fracture apertures are significantly higher than the other fluids. So we do see that polymer solution reaction with CO2 generate higher conductive fractures than water, independent of the flow rate, CO2, or water CO2. Thin sections, like I say, for water saturated rock, we are pending the results. And then here, this is a diagram of the conductivity as a function of breakdown pressure. We observe that at higher breakdown pressures, the conductivity does increase. But in the case of water saturated rock for 3 days, the triangle, independently of the fluid we use, and this is just all the fluids, the conductivity is very low, with one exception. Polymer solution CO2 got a conductivity in the order of 20 cubic micrometers, 5 cubic micrometers, still low, but higher than the rest. As the water saturation reduces, and we're talking about the red dots, or hot dry rock, no water whatsoever in the rock, the values of conductivity significantly increase. And these values right here correspond to the polymer solution CO2. These ones here are corresponding to water CO2 or CO2 alone, and these are for water alone. Water alone, even in hot dry rock, the values of conductivity are very small. So we're trying to understand a little bit of, okay, why we get higher fracture conductivities with polymer solution CO2 reaction, and trying to understand a little bit about, okay, if it's not a plug that is formed and a volume expansion of that plug to radially to generate an overpressure in addition to the pressure exerted by the pump, why we are able to generate a higher fracture conductivities, even though the breakdown pressure is similar, the fracture conductivity is higher. So we did some stump modeling, simulated pressure distribution curve here. So the stump is a subsurface transport over multiple phases. This is a code that was developed at PNNL and by Mark White and Mark Ostrom. And I will not get into details, but what this model does is we simulate, this is 1/4 of the total rock, and this is a simulated notch. And then we have the packers on each side. and then we let the fluid to penetrate the rock, and we get an idea of the pressure distribution as a function of distance from the wellbore to the wall of the rock sample. And what we see for 10 milliliters of water, 10 milliliter flow rate, sorry, 10 milliliter per minute flow rate of water, 10 milliliter flow rate per minute of flow rate of CO2, or introducing water followed by 10 milliliter per minute CO2, or introducing polymer solution followed by 10 milliliter per minute of CO2, is that the pressure distribution, this is the dotted line, means the minimum pressure stress. So this is the minimum pressure required to fracture the rock. You can see for water across nearly the entire sample, the pressures at any given time are below, significantly below the minimum pressure required to fracture the rock. In the case of CO2, yeah, we have a longer distance at which the pressure is higher than the minimum principal stress, or the minimum pressure required to fracture the rock. And then for water CO2, same thing, a little bit more maybe. It gets all the way to 3 centimeters. But in the case of polymer solution, we get a much higher, even at very low, at very beginning of the reaction, or when we introduce CO2 with water, we get pressures above the minimum principal stress significantly higher than the other 3 fluids. And it goes all the way to about 3.5 centimeters from the wellbore. So what we believe is that the higher viscosity associated to the reaction of PAA with CO2 reduces the propagation of pore pressure. So it results in a broader region with elevated pore pressure. And that could be, it's just a hypothesis, could be the reason why we generate higher conductive fractures as compared to either water alone, CO2, or water CO2. So this is switching a little bit gears, and I'm almost done with all the slides, and worry about that. So what the short-term technology office wanted to know is, okay, yes, you can generate fractures. You can generate fractures more conductive than the other fluids. That's great. And in respect to water, about between 2 and 3 orders of magnitude more conductive. That's great. But this is a small sample. How you will do this, and like I mentioned before, hundreds of meters away from the wellbore. So one way to do that is, like I say, the polymer alternating gas, or water alternating gas, but in the case of polymer PAG, is polymer alternating gas. And getting fresh CO2 and fresh polymer solution going towards the tip of the fracture and continue propagating the fractures. And that's something that we can only do in the field. We cannot test. It's really hard. We try, but it's really hard to do it in a rock sample of a sculpted foot. The second approach, instead of the water alternating gas, or polymer alternating gas in this case, is self-diversion. Can we generate a fracture? And in this case, this was proposed by Chef Burger, a team member of ours. He's a geophysicist, a very smart guy, and he may say, okay, in addition to propagating the fracture farther from the wellbore, what about if you need not a single fracture, you need a complex system, or a complex network of fractures to avoid, cooling down the system too fast, right? We want a natural radiator. We don't want a single fracture communicating between the production and the injection wells. So then he thought, okay, can we use the fluid to generate a fracture, and the reaction, the cross-linking reaction, generate an actual shell, a shell that will actually plug. It does look like the one that the polyallylamine 17K Dalton is not good for that, to generate a plug at least. It does increase the volume, but by reaction with CO2, but it does not form a plug. What about if we explore other chemistries that can actually generate a plug, fracture and plug that fracture, and then we introduce a second fluid, let's say CO2, that will find that plug and then generate secondary fracture away from that main fracture, and in that way have fractures that are more complex than just a single fracture. And we found another polymer. It's not the polyallylamine, but it's this polymer that in reaction with an epoxide form a cross-linking. It doesn't require CO2, but it requires temperature. At higher temperatures, this reaction occurs very fast and forms a shell. And we did it in the lab at 90 Celsius, that's a room pressure. And then we tested that plug. What about if we mix this epoxy with amine, and with the amine, we take CO2 to push that solution into a coil, a 1/16 of an inch tubing that will simulate a fracture of about, I don't know, 1/18 of an inch in aperture. And then we see if that plug will form and not move. And indeed, once it reacted at 200 Celsius, we increased the pressure with CO2 after reaction up to 6,000 psi. We stop here, and there was no change. There was no movement of that plug from the coil. So the goal now is, can we perform that reaction in a true triaxial frame in natural rock sample? Can that reaction form, fracture the rock at the tip of the wellbore, let's say, form a plug, and then we inject CO2 to generate a secondary fracture? That's part of the next part of this project. So in conclusion, I presented StimuFrac. StimuFrac is a polymer solution that reacts with CO2. That's why it's a stimuli-reactive polymer. Expands in volume. That expansion in volume as well as increasing viscosity is reversible in nature. So it can be used to fracture, and then it can be recovered, that polymer solution, for reusing second wellbore if possible, together with CO2. In confined environment, we were able to show that it does generate work. We were able to measure the pressure, but it doesn't seem that form a shell that will confine that pressure so it can generate a local radial pressure to get lower overpressure to fracture. But it does, yes, fracture rock more efficiently in terms of fracture conductivity compared to water, CO2, or combinations of water and CO2. And with that, I would like to thank my team and you guys for the patience to go through all these 7 years of work, and the Government Technology Office for the funding and the support. Thank you very much.
Thank you, Dr. Fernandez, for an excellent presentation. For the audience, if you've got questions, please use the raise my hand facility, and I'll call on you by name, and you can unmute yourself and ask your question. So we've got a question from Julian.
Hello, Carlos. I enjoyed that very much. I missed the very first part. Did you talk about the cost of the fluid StimuFrac versus alternatives? Or is there a way to even cost it out at this point?
Yes, I did not talk about it, and that's a great question. We did, obviously, anything that you add to water will increase its cost, right? And even if it's 0.001%, is going to be more expensive than water. But the important thing here, so the value for this fluid, so the value of the polymer is about $1 a kilogram. So it's fairly inexpensive. But again, if you add it, in several cubic meters of water, you introduce a higher cost than the water alone. But if we were talking about cost versus efficiency of fracturing, in talking to our collaborators in Alta Rock and Silk Energy, they say this fluid has the potential to reduce the amount of wire required to fracture. For geothermal applications, they are using, I don't want to say a crazy number, but we're something in the 40 million gallons per wellbore to fracture. And they estimated with our fluids to cut that in about half. So water cost is a big issue, particularly in dry areas. So if we can, introducing this small amount of polymer, reduce that in any way, even if it's a fraction, not half, will eventually be much more effective, cost-effective than using water alone. Obviously, you also use the CO2, right? And we did some, I can provide with that information. I have a table with the cost of CO2, the cost of the polymer, and how that, in the long run, if you have to do a stimulation of wellbores, you end up saving money because of the water that you reduce.
Thanks a lot. Yeah, it didn't appear like it's, I just wanted to know if it was like a significant increase in cost for this, but it doesn't look like it is at all. Thank you.
You're welcome. Thank you.
Lucas.
Hi, Dr. Fernandez. Really great presentation. I missed the first bit, so I think I might have missed this. Is during these tests for both water, CO2, and the combination, is propant used? And if it's not, why so?
Good. Very good question. So propant is a very interesting discussion that we have with geothermal community. First of all, propants at these temperatures, they haven't shown to survive. But not only because of the stress associated, the mechanical stress that the propant has to undergo, which is also the case for oil and gas industry, where propants are used most of the time, if not all the time. For geothermal, it's really, really hard because of the high temperatures. But what we observe, and this is something that was observed in all these years of working with StimulFrac CO2, is that it looks like the fracture form is a self-prop fracture. So we, in principle, will not require propant, because if there is a slight displacement, and again, this is just what we observe, it's not, it hasn't been proven, but we observe that the material post-mortem, as well as right after we measure the conductivity, right after we stimulate, we measure the conductivity, and we observe that the conductivity of the values of conductivity of the using water for the rock samples fractured with StimulFrac CO2 are similar to the value of conductivity post-mortem. So when you release that pressure, when you cut that rock, you get very similar values. So that means that that fracture doesn't close after we release pressure of the fracturing fluid. So it's a self-prop fracture. By having said that, yes, there is a lot of work around propants for geothermal. We have a technology that we have patented, but we haven't been able to yet. We just have proof of concept where we look at propant aggregation. It's called StimulProp. Instead of StimulFrac, StimulProp. It's a propant that has a polymer shell, and when it reacts with CO2, that those polymers can bring together and they agglomerate the propants and prop the fracture. In principle, prop the fractures open. We have a paper on that. But propants for geothermal is a big deal. We haven't seen anything in the field, or at least I'm not aware of the use of propants in geothermal environments because of the high temperatures and because of the instability of the propants.
Would something like sand work? I know at least in Midland and places like that, generally sand is used as a propant. Is that something considered?
For oil and gas, yes. For geothermal, sand will not survive, and there is a slow dissolution, and when you have dissolution and then potential precipitation of silica farther into the formation in smaller aperture fractures, then the propant, instead of becoming a solution, becomes a problem because it plugs the wellbore, not the wellbore, sorry, the fracture network. Sand is something that will not work. What they have been looking at is sintered bauxite. It's very high temperature treated bauxite, which is a mineral. But again, the work by Shaw Moore at University of Utah demonstrated that at least 30 days, sintered bauxite is very sturdy, even at high temperature propant. But like I say, even though after 30, 40 years in the geothermal field, not need, the propant are a big problem. They still need to develop them.
Thank you. That's very interesting. I'm surprised. Yeah, very surprising. Very interesting. Thank you.
All right. More questions for Carlos? Maybe while people think of more questions, I've got a comment and a question. Yeah, you know, viscosity dominated propagation, you know, versus toughness dominated. You certainly would expect to see these larger apertures, you know, even just from classical solutions. So, you know, and looking at the pressure profiles that you simulate, you know, they resemble very much what you'd see from a viscosity dominated propagation. Exactly. Yeah. And a question on the true triaxial cell. Were those experiments conducted at in situ conditions, particularly temperature?
Yes, Rami. So the experiment, the rock is heated overnight, and we have several thermocouples inside the rock that basically provide us with an idea of how homogeneously distributed is the temperature inside the rock. So by heating overnight that rock, we get 200 Celsius in about 14 hours, and then we wait another 3-4 hours to begin the experiment. So the heating is in situ, and then the pressures we use flat shocks, and these are kind of like bladders made of metal. They come from Italy, and we fill them with oil, and this is again work that Chef Burgar, Guo Qingxian, and the team have been performing. And those bladders swell a little bit and exert pressure in both axial directions and then radial directions, and then on the axial pressure is exerted by the frame. I don't know if I answered your question, but yeah, everything is
Yep.
Celsius.
Yeah. It's you know, I think we have Dr. Azbayoglu on the call. You know, he has a true triaxial cell cubic foot. You know, I was just curious how you handled the temperature component. So as a follow-up question, how do you saturate granite?
All right. So yeah, that's it. You know, you will think granite will take a long time to to absorb water, and what we observe, and this is, let me see if I have the here. So what we do is we inject water, so we heat the rock at 200 Celsius overnight, like you mentioned. That rock will have water. Obviously, the granite is not completely dry, so it may have some water even after heating up for overnight. But and we see sometimes water vapor coming out. But then when you inject water at 1,000 psi, that's we chose that pressure just randomly, and we keep that pressure for 1 day or 3 days, we can see that the flow rates continue increasing as the rock gets more and more saturated with water. So the leak off of water into the formation rock, in this case, this granitic specimen, is much more is higher than we expected, we anticipated, due to the porosity, right? It's a 2% porous rock, and it flows, water flows at, you can see here 1 milliliter per minute all the way to about after 2 days or 3 days, you get close to 3.5 milliliter per minute, which is a typical leak off of water into highly low porosity rock samples. I don't know if I answered the question, but
yeah, no, that's awesome. I'm just surprised.
yeah, and I think it's a pressure, right? If you put the rock sample in a bucket with water at room pressure, it may take months.
Yeah, I think, Carlos, we lost you there for a second.
Can you hear me now?
Yeah.
So what I was saying is, if you dump this rock in a bucket of water at room pressure, it would probably take a long time, months, for this rock to become fully saturated. And I'm not saying injecting for 3 days at 1,000 psi will saturate completely the rock, but definitely we can see that there is a very high flow rate after 1 or 2 days associated to basically the transport of water into the formation. So even though granite is 2% porous, it's pretty permeable.
Perfect. So we've got time for maybe one more question. We've got Lucas again. Lucas, is your hand up?
Hi. Yes, I have a question. Dr. Fernandez, when you guys are injecting your, I think it's a polyacrylic polymer, do you do that with pure CO2? And
Sorry.
yeah, do you ever do that with just pure CO2?
No. So the injection is, I don't think I went into detail, but the injection is similar to what we do with water. We, instead of putting 1,000 psi, if I remember correctly, it was around 1,100, 1,200 psi. It's just enough pressure above the 1,000 psi for the PAA to leak off. Okay, similar to what water does. We check it at constant pressure, and what we do is we stop after we estimated the volume of the rock being the pore volume being about 33 milliliters. So based on surface area analysis and volume of the entire sample, and then we say, okay, we're going to sit at 1,100, 1,200 psi constant pressure with polymer solution and let it leak off inside the rock until the pump shows about 1/3 of the volume has been delivered. Okay, so that I think is shown in this next slide. So we let it at 1,100, 1,200 psi. So the polymer solution will get a little bit diluted because you have water in the rock, it's water saturated rock. But you have probably some distribution like this across the entire sample. And then we introduce CO2. We stop that pump, we close the valve, and we swap to CO2 pump, and we introduce CO2 at constant flow rate until the fracture occurs. And what we see, and unfortunately, I'm sorry, I forgot to put a slide. What you're going to see is basically the pressures, the flow rate is constant, but the pressure increase, and then boom, it falls down. And that is when the fracture has gone all the way to the surface of the rock, and then it needs atmospheric pressure. So what we see is just the pump pressure going down, and then a lot of fluid coming out of the rock. At that point, we stop the experiment.
Okay, thank you.
Sure.
All right. So we're just about out of time for the seminar. On behalf of the folks at TU MSPE, thank you very kindly, Dr. Fernandez, for an excellent graduate seminar. And we hope to host you in person sometime in the near future here at TU.
Thank you, Rami. No, thank you for the opportunity. I hope that we can have everybody sleeping, put into sleep, and you got something out of this. And feel free to contact me directly or contact you, Rami, students, if they want papers to be sent to you. If you want this presentation, I can definitely prepare that for you in PDF. And thank you again for your attention, and I hope you have a great weekend.
Thank you. Carlos, do you have a few minutes to chat, maybe as people sign off in a minute or two?
Yes.
Awesome, awesome.
By the way, Julian Chestnut is my boss. he goes with the name Natman.
Ah.
Yeah. See, here PNL. But I probably this was the first time he listened to the presentation.
Awesome.
Yeah, really enjoyed it, Carlos. It's awesome.
Thank you, Julian. Thank you, Natman.
Yep. Take care. Cheers.
You too. Have a nice weekend. So what's the plan for the weekend, Shun and Rami? Is working on the proposal, I bet.
Proposal writing, that's exactly right. And, you know, a bunch of other things, but
Well,
mostly
course,
proposal writing, so.
Yeah, that's crazy.
Let me just...
Yeah, Rami, you can stop recording.